Okay, welcome back. This is Israel again. So, electrolysis of concentrated sodium chloride brain using mercury electrodes. Now, if you have not forgotten what I said earlier, I told you that and some electrodes are active while some are inert. So, inert electrodes, they just perform their job as electrodes, while active electrodes, other than performing their job as electrode, they also influence preferential discharge of certain ions that they have affinity for. Now, an example that I gave, one of them is I gave mercury as an example. So mercury has affinity for sodium. So that is to say, if you are using a mercury electrode, wherever you see, maybe you are using, you are dealing with an electrolyte that has sodium in it. Once you are using mercury electrode has affinity for sodium. So it is going to unpick sodium and then discharge sodium like at the expense of the other one. So from what we have been doing before, so for electrolysis of concentrated sodium chloride using mercury electrode, for the first step, ionization of the electrolytes and water. This is what we have here, Na plus, Cl minus, this. Don't forget that it is concentrated, meaning that we are going to be having high concentration of sodium and then high concentration of what? Chloride ion. Now, migration to the electrodes. So this and sodium ion and H plus, they migrate to the cathode, Cl minus and OH minus to the anode. This one's to the cathode, the remaining two to the anode. Now, what happens at the discharge? So, at the discharge, looking at the statement now, position of the ion in the chemical series will matter. Yes. Concentration of the electrolyte will also matter because the electrolyte is concentrated. Now, nature of the electrode will also matter. Why? Because we are using an active electrode, which is mercury. Now, so we have Na plus here and H plus. Which of the two is going to be preferentially discharged? Now, Na plus and H plus. Na plus has higher concentration rather compared to H plus. But because the distance is both of them very far, so concentration will no more matter, considering these two ions. But position of the electrochemical series, H plus is down, Na plus is down, Na plus is down, and Na plus is up. But for nature of the electrode, you are using mercury electrode, which means that mercury has affinity for sodium. So, in spite of every other factor, nature of the electrode is going to be the what? Going to be the determining factor. Why? Because mercury has affinity for sodium. So in this place, H plus will not be preferentially discharged, but Na plus will be discharged instead. Why? Because we are using an active electrode, which is what? Mercury electrode. So just notice that anywhere you see mercury and then you are dealing with an electrolyte that has sodium in it, once you have mercury electrode, know that mercury will preferentially go for sodium. So making sodium to be preferentially discharged. So in this place, sodium ion will be discharged, Na plus, meaning that we'll be having, this is a reaction, Na plus E minus to give you Na solid. So what's happening? Sodium ion gains an electron and becomes sodium metal because gain of electron is reduction and is occurring at the cathode. So this sodium ion gains an electron to become the neutral sodium metal. So now let's go to the anode, Cl minus and OH minus, chloride and OH. Now, nature of the electrode, mercury will have nothing to do in this place because it doesn't have affinity for any of these ions. So nature of the electrode will not matter. Now, concentration of the electrolyte will matter because Cl minus has higher concentration, because sodium chloride from which Cl minus is gotten from as is highly concentrated, is concentrated. So now, between Cl minus and OH minus, you can see Cl minus is here, OH minus is here. Normally, OH minus should be discharged because of its position in the electrochemical series. But because Cl minus has higher concentration, it will be discharged. And then the distance between Cl minus and OH minus, the distance is between just two other ions, Cl minus and I minus and Br minus. So Cl minus will be discharged. So at the anode, we'll be having 2 Cl minus to give you Cl2 plus 2E minus. Now, at the anode, we have Cl minus being discharged, meaning that chlorine gas is being produced. So Na plus is out, then Cl minus is also out. Now, what do we have left? We have H plus and then OH minus remaining, meaning that H plus and OH minus can combine to give us our what? To give us our water being formed. To give water being formed. So that means at the end of the reaction, So H plus and OH minus, both of them will combine together, giving water. So nothing happens to the solution. Everything is just neutral. Because H plus will be completely neutralized by OH minus. That will give us water. pH equals to 7. Nothing is going to happen. So Na plus, sodium metal is being formed at the cathode, chlorine gas is being produced at the anode. So that's how that one occurs. Now, checking through your syllabus, I have another example here. That one is, well, they're asking us to do electrolysis of aqueous copper 2 sulfate. Electrolysis of aqueous copper 2 sulfate. Electrolysis of aqueous copper 2 sulfate. Copper 2 sulfate is CuSO4. Electrolysis of aqueous CuSO4 using platinum electrode, that is our inert electrode. Now, what do you have here? CuSO4 aqueous. So this one we undergo, we have our Cu2 plus SO4 2 minus. Then we have H2O. That one will give us, we have H plus OH minus. Now, at times in some UTME questions, and then you only see aqueous. Anytime you see aqueous, assume it to be dilute. Okay? So if it is concentrated, they always put concentrated there. But at times they might not put dilute. So once you see aqueous, just assume that it is dilute. So just use dilute format to do everything you are doing. Yeah, because it is aqueous CuSO4, this one and this one, Cu2 plus and H plus, they migrate to the cathode, and then SO4 2 minus and OH minus, they migrate to the anode. Now, what we have is that discharge. What will be discharge now? We need to check the electrode we are using. If you are using inert electrode like platinum or like graphite electrode, nothing will happen. Electrode will not affect, will not influence the discharge of any ion, meaning that this one will have no part to play. Now, but because this electrolyte is aqueous, so this one and this one, these are Cu2 plus and H plus, they are going to the cathode. Now, which of them will be discharged? Now, the electrolyte is not concentrated. They say it's aqueous, so aqueous dilute. So when you say aqueous, they are talking about that. So concentration of the electrolyte is nothing in this place. So what will only matter? Position. So check Cu2 plus and H plus. Which one is below in the activity series? The one that is below is what? The one that is below is actually Cu2 plus. Cu2 plus is below H plus. So which one will be discharged? Cu2 plus. So at the cathode you'll be having Cu2 plus 2E minus to give you copper metal. That is copper ion, copper 2 plus, 2 ion gains 2 electrons to become the metal. Now, let's go to the anode. What happens at the anode? Now, the solution, the electrolyte is aqueous, so because it is aqueous, no concentration of the electrolyte is not going to do anything. Nature of the electrode, we are using platinum electrode, is inert, nothing will happen. So what we only determine the ion to be discharged, position of the ion. So checking SO4 2 minus and OH minus. OH minus is down. So because it is below SO4, OH minus will be what? Discharged. So at the anode, so what are you going to be having? 4OH minus, the equation I told you guys to memorize the other time, to give you 2H2O plus O2 plus 2E minus, plus 4E minus rather. Now, so we can see that at the anode, OH minus is being discharged. At the cathode, Cu2 plus is being discharged. H plus is being left in the solution. And then SO4 2 minus. Both of them can come together to give you an acid, a strong one. I guess to give you a strong acid. So that means at the end of everything, the resulting solution that you'll be having will be what? Acidic. Because you still have H plus being left in the solution. So it will be what? Acidic. So at the cathode, what is being produced? Copper metal. At the anode, what is being produced? The gas that is being produced is oxygen. So you have water and oxygen. So that's the way the reaction goes for this one. Now, let's assume that we are using copper electrode. We are using copper electrodes. Electrolysis of aqueous CuSO4 using copper electrode. Now, you are going to be having a different thing here. You are going to be having a different thing here. So what will happen? Now, we know the ions that will go to the cathode, Cu2 plus and H plus, we go to the cathode. And then we have our OH minus and SO2 minus, SO4 2 minus going to the anode. Now, what will be discharged at the electrodes? Now, we are using copper electrode. That is to say, our anode is made of copper rod. Our cathode is also made of what? Copper rod. Now, whenever you have your electrode being a component of the electrolyte. When your electrode is a component of the electrolyte, what you'll be having is that you eventually be forming that metal in your electrolyte. That's what you'll be getting eventually. Now this is what? Copper 2 sulfates, copper 2 tetrasulfate 6. Then you are using copper electrodes again. So that means in the long run, at the end of everything, you still be getting copper being discharged at both electrodes. So this is the way it occurs. Now at the cathode, what will happen? Because you are using copper electrode, what happens is that copper will be discharged. You are comparing copper 2 plus and H plus, so copper will be discharged. So you'll be having Cu2 plus 2E minus to give you copper solid. Now, what happens at the anode? Something funny happens at the anode. The funny thing that happens at the anode is that at the anode, don't forget that at the anode you have your anode is made up of copper rod. Now, what happens is that because oxidation occurs at the anode, which is copper in this case, it begins to wear out and it goes into the solution. Now, it begins to wear out. So let's assume that this is your electrolytic cell. This is the cathode, I represent it with C. This is the anode, I represent it with A. Then this is your electrolyte, CuSO4. Both electrodes are made up of copper rod. This is copper rod, and this one is also copper, Cu solid. Both of them. Cathode is copper, anode is also copper. Now at the anode, we know that copper will be discharged because Cu2 plus and H plus. So copper is below and even because of the nature of the electrode, the electrode is copper, and then we are dealing with the electrolyte CuSO4 that has copper. So copper will be what? Copper will be preferentially discharged at the cathode. Now at the anode, we have SO42 minus and OH minus. Because the anode is a component of the electrolyte, none of the ions here will be preferentially discharged. It is that copper anode that will be what? That will go into the solution. And then eventually, this copper anode that is here, it will be wearing out into the solution. And then as it's coming out, it's going to be depositing on the copper cathode here. Now, the copper anode, normally, as we have been doing before, we check the ions and then one of them will be preferentially discharged based on some factors. But because the anode is copper and the electrolyte is also a compound, a salt of copper. So what happens is that at the anode, the copper that is the anode, it begins to go down into the solution. It will be wearing out. It will be wearing out, and then as it's wearing out into the solution, it will be depositing on the cathode, meaning that the anode will be reducing in size, will be reducing in mass, and what will be happening to the cathode? Cathode will be increasing in mass. The copper from the anode will be depositing on the cathode. So as you continue the reaction and all, what happens is that the anode will be wearing out, the mass will be reducing. Let's say we start with 5 grams before. Now, after some time, the 5 grams will be reducing little by little, maybe to 4 point something, and then small. And then the cathode, don't forget that the cathode is also copper. This one will be increasing in size. So that's what happens. So at the anode, what will you be having? You'll be having you have your Cu solid to give you Cu2 plus 2E minus. Why is this reaction? The copper is going down, cathodic reaction, oxidation, this one is going down, and then it's deposited on this. So you have this. So at both electrodes, anode and cathode, what happens is that it's copper that you are getting. So, and then one thing that is very important, whenever they ask you electrolysis of aqueous CuSO4 using copper electrode, is that the anode will be reducing in size, in length, in mass, while the cathode will be what? Cathode will be increasing. So that's because the anode will be going down into the solution and will be depositing on the cathode. So that's the most important thing that happens. So the last example on this aspect, according to your syllabus, is the electrolysis of aqueous copper 2 chloride, CuCl2. This one, you just follow everything we have been doing. So aqueous copper 2 chloride. So this one, let's say this one is copper 2 chloride, CuCl2 aqueous. So this one will give you Cu2 plus 2Cl minus aqueous. Now this one will be H plus and OH minus because it's water. Now, what are we going to be getting? We'll be having a discharge, OH minus, because it is lower. So when OH minus is discharged, what do you have left? Cu2 plus is gone, OH minus is gone. We have H plus and Cl minus remaining. That one will form a very strong acid, meaning that your pH will be less than 7. The resulting solution is acidic. So that's how you solve questions relating to electrolysis. Now, going further, we want to check Faraday's law of electrolysis. Actually, Faraday is the founder. Faraday actually founded electricity that most of us use today. And then in electrolysis, he actually gave us two laws. He postulated two laws, which I'll be giving us now. So we have the Faraday's first law of electrolysis, and then we have Faraday's second law of electrolysis. Faraday's first law of electrolysis states that the mass of a substance deposited at during electrolysis is directly proportional to the quantity of electricity that passes through the electrolytes. Now, the mass of a substance being deposited at electrolysis is directly proportional to the quantity of electricity that passes through the what? Through the electrolyte. Now, let's assume that our electrolyte is CuSO4. That's copper 2 sulfate, CuSO4. CuSO4 will give copper metal because this is the copper. In CuSO4, you have copper ion, and then at the cathode, copper metal will be deposited. So, the mass of copper that will be deposited will what? Directly proportional to the quantity of electricity that passes through this electrolyte. So this is what we'll be having. We'll be having this mass deposited M directly proportional to the quantity of electricity. The quantity of electricity is Q. So, and then Q equals to IT. That is Q equals to I times T. What is I? I is current. Quantity of electricity. So Q equals to I times T. So this quantity of electricity is represented in, we have in coulombs. So it is in coulombs. So when you see something coulombs, that means they are talking about quantity of electricity. Now, I is our current in amperes. T is our time. Oftentimes in seconds because that's the SI units of time. So M is directly proportional to Q. So we'll be having, bring our constant, M equals to ZQ. This Z is the constant, which we call electrochemical, we call it electrochemical coefficient. So electrochemical coefficients. Now from this place you have M equals ZQ. So since we know that Q equals IT, you can bring it in. So M equals to what? ZIT. So it can give us the electrochemical equivalent of the metal we are dealing with, the current, and then the time. So we get the mass of the substance deposited at electrolysis. So that is Faraday's first law. Now let's go to Faraday's second law. Faraday's second law of electricity states that when the same quantity of electricity is passed through what? Is passed through, we have different solution of electrolytes arranged in series. When the same quantity of electricity is passed through different electrolytes arranged in series, the quantity, the number of moles of the substances being deposited is inversely proportional to the chemical equivalent of whatever we are dealing with. Now let me come again. Faraday's second law of electricity states that when two electrolytes, when same quantity of electricity is passed through two different electrolytes arranged in series, the number of moles of each substance deposited is inversely proportional to the chemical equivalents of the metals we are dealing with. For example, now let's say we are considering two salts, AgNO3 and CuSO4. Both of them are salt, both of them are electrolyte. They can break down to give ions. Now from this now, this one, the metal here that we have is silver, that is Ag. And then the metal here is, this one is copper, Cu. Now, silver is univalent, meaning that if you check our electrochemical series now, you see somewhere Ag plus. Silver is univalent, meaning that the number of moles, the number of moles of each substance deposited is inversely proportional to the chemical equivalent. So on silver, the chemical equivalent is 1 because it is plus 1. Whether it is minus 1 or plus 1, the sign does not matter, so it is 1. For copper oftentimes is 2. Copper is 2, so copper will be what? 2. Now, for zinc, let's say you have a compound of zinc. Zinc is also 2. Zinc 2 plus. We can have Fe 2 plus. We can have Mg 2 plus. Now, so this is the representation of Faraday's second law. You have something like this. Number of mole of each substance deposited is inversely proportional to the chemical equivalent. That is N inversely proportional to 1 over Q. This Q is their chemical equivalent. So we can say N is equals to K over Q, meaning that NQ equals K. So we can say N1Q1 equals to N2Q2. N2Q2. Now let's assume that we are considering two electrolytes. The one we have, let's say we are considering Al2O3 and CuSO4. Al2O3, that one will give you aluminium, and aluminium is trivalent. Al3 plus is here, aluminum is trivalent, Al3 plus, and then copper is divalent, Cu2 plus. So this one is Cu2 plus, this one is Al3 plus. So for this one we can represent it and say NaL QAl, this for aluminum, equals to NCu QCu. This will only be appropriate if the same quantity of electricity is being passed through these two solutions of aluminum and copper. So now they can give us a question that we should calculate some. Maybe they give us the mass of aluminum being deposited. Let's say they give us something like 2.7 grams. Then they give us the mass of copper being deposited. Let's say, okay, we want to find the mass of copper being deposited. But for aluminum, the mass of aluminum being deposited is 2.7 grams. Then for copper, they're asking us to find it. So how do we do it? You use this formula. N1 equals to Q2. So you can, let's say this one is for aluminum. Number of mole is equals to mass over molar mass. You can get that. So from here now, we calculate the number of moles of aluminum, saying number of mole equals to 2.7 grams. But because this one now, aluminum is an element, so we use the atomic mass, 23. 2.7 divided by 23 grams, so we get the answer, number of mole of aluminum. We can now bring it into this place. So to bring it into this formula, it will be, for aluminum, it will be N, which is 2.7 over 23, multiplied by, what is the chemical equivalent of aluminum? Is Al3 plus times 3, that 3 that is there. Whether it is plus or minus, it doesn't matter, times 3, equals to, what of copper? Number of moles, we don't know. Let's call it N. Then what is the chemical equivalent of copper? 2, because copper is 2 plus. That 2 times 2. We can now find the number of mole of copper here, and after getting the number of moles, we now say number of mole equals to mass over molar mass. So because you know that for copper, the atomic mass of copper is 63.5. So after getting N, we will now do N equals to M over 63.5. So our N, we can get it from here. N is equals to, if you do our mathematics well, that will be what? 2.7 times 3 over 23 times 2. So we can get our answer. That will be our N. So after getting our N, you come here to get the mass of copper being deposited from this equation. So that's how you do simple equations that are in electrolysis. So we are going to get there, we'll solve more questions there. Now, let's go to application of electrolysis. How do you apply electrolysis to, like, in real-time life? What are the applications? Now, under the application of electrolysis, there's what we call electroplating. There's what we call electroplating. Electroplating. Now, from the word electroplating, we have electroplating. Now, electroplating is actually a method that we use to actually prevent or reduce the rate of corrosion, or to improve the aesthetics of our metals. Now, a lot of us, we use spoons at home, and we see that the spoons that we use, they are always shining and shining. The spoon is not just metal, it's not aluminum or anything. That spoon has been electroplated. So they applied silver to it, so that's why it's making it so compelling to you. It was that thing that made it so compelling for you, like to you guys to buy. Now, so electroplating, what do? We coat metals, we put some things on metal just to improve the durability or to make it more beautiful. Now, so what do you do in electroplating? For example, let's use our spoon, our silver coated spoon. What are we going to do? So whatever you want to electroplate, that thing that you want to coat, you make it the cathode. Now, what you want to put as coating on it, you make it the anode. And then you make sure that the electrolyte is a salt of the anode. Now, for example, let's assume that this is our spoon. Normally, I was just crude spoon, and then I want to make it to be shiny. So let's say I have my spoon on the left. Now, this is silver that I want to put on it. This spoon will be the cathode. Now, what I want to put on it is silver. That means this spoon will be the cathode, that silver will be the anode. Now, the electrolyte will be a salt of the anode. So, and a salt of the anode, that is a salt of silver that we can easily use, is silver triazonitrate. We can use silver triazonitrate 5. So now, that is to say, at the cathode we have spoon, cathode. Then at the anode we have our silver. Then the electrolyte that we'll be using will be a salt of the anode, a compound of the anode, which could be something like AgNO3. So what happens is that at the end of the electrolytic reaction, the silver, now don't forget what we explained under electrolysis of CuSO4 using copper electrode. That I said that at the anode we use the anode, the copper will go down to the solution and it will be deposited on the cathode. So that's what will be happening here too. You can see that we are using silver anode and then the electrolyte is a salt of the anode. So what happens is that this silver will be going into the solution and it will come and coat the spoon. So eventually what are you going to be having? From crude spoon, there's going to be a transformation to what? Silver coated spoon. So that's why after the end of the reaction, this silver comes and then it coats this spoon so that every part of the spoon it now becomes like coated with silver, so it's now be shiny. So if they are to market crude spoon to anybody, like Amisos now, nobody will be able to buy that spoon because it will not be looking appealing. But because we have performed and something that we call electroplating, one of the applications of electrolysis, the spoon becomes something that looks fine to us and then we buy it. So that's electroplating for you. So whatever you want to electroplate, you make it the cathode. What you want to plate it with, you make it the anode. And then you make sure that the electrolyte is a what? Is a compound or salt of the anode. So that's the way it's been done. So they can say, okay, you want to coat iron. For example, I'm just assuming you want to coat it with gold. I'm just assuming iron, you want to coat it with gold. So what will be the cathode? Iron. What you want to coat? What you want to electroplate? Now, what will be the anode? That thing that you want to put on it, which is what? Gold. Now, your electrolyte must be a salt of the anode. That is a salt of gold. So that at the end of the reaction, gold will come on iron and then it will be covered with iron. So covered with gold. So that's one of the applications of electroplating. Another one is purification of metals. You can use electrolysis to what? Purify metals. Now, so you must have heard of what we call electrolytic reduction. Metals like iron, metals like sodium, metals like potassium, metals like calcium, they can actually be derived from or gotten from electrolytic reduction of their hulls or their salts, as the case may be. So now you can use it to purify metals. Also, you can use electrolysis to manufacture some molecules and some compounds. For example, now if you check the examples that we did back then, we could see situations whereby we got sodium metal, situations whereby we got oxygen gas, situation whereby we got hydrogen gas, Cl2. So we might not know. That means we are manufacturing some compounds or molecules, as the case may be. So you can use electrolysis to actually prepare some compounds like that. Now, another thing that you can use electrolysis for is that there's what we call cathodic plating. Cathodic plating. Now, every metal undergoes corrosion. Every metal undergoes corrosion. But the corrosion that is specific to iron is what we call rusting. So when we say rusting, that is the corrosion of iron. So every metal corrodes. But the corrosion of iron, that's what we call rusting. Now, how does rusting occur? Rusting occurs when you bring in your metal, your iron, and then you expose it to a place whereby whereby there is oxygen available and then there is moisture or water. So when you have moisture and oxygen and air, so what happens is that there is a formation of rust. Now, rust is actually iron 3 oxide, hydrated iron 3 oxide, Fe2O3.3H2O. This is what we call iron 2. So this is iron 2 trioxide, and then this is what? Trihydrate, because we have 3 molecules of water here. So what are the conditions necessary for rusting? Your metal must be present, your iron, I'm talking about iron now, and then moisture must be available, and then air or oxygen must be available. So when you have your iron 3Fe plus H2O, to balance the reaction, eventually you'll be getting this. This is what we call rust. That's that thing that forms on your iron. That thing that forms for those of you that use cutlass. So if you put your cutlass after using it, you now put it outside, you now come back after some days. If you check it, you see the formation of something like slimy, something like reddish brown in a form like this. So that is rust. So you can actually prevent rust or reduce rust by what we call cathodic protection. Cathodic protection. Cathodic protection is actually similar to electroplating. But the difference is that, don't forget that in electroplating, what you want to electroplate, that's the cathode. And then anode is what you want to put on it. Why the electrolyte is a salt of the anode. But in sacrificial cathodic protection. What we do is that what you want to, like let's say the iron now, you don't want the iron to rust. So it is the iron that you make the anode. So you use another metal, a more reactive metal. That is to say, you check your activity series. You must make sure that the metal is above. Don't forget that I was explaining that if you have the activity series, those ions that are above, they are more reactive than the one below. So you use a more reactive metal to put on it. That's what you put on it. So for example, now let's say you want to do cathodic protection for iron. We can use a metal like zinc. You can see iron is Fe2, zinc is above it. So you use zinc. So the iron is the anode, zinc is the what? Cathode. Zinc is the cathode. So eventually what happens is that the surface of the iron becomes coated with the zinc. So that even if you put it outside, you know, it is moisture and water, moisture and oxygen that will react with the iron, and not the, so they will meet the zinc surface on top of it. So that one will not allow it to rust. So those are the uses of electrolysis as far as this course is concerned. And then so let's go to calculation in electrochemistry. Very simple calculation. So here we'll be talking about a part of stoichiometry, talking about Faraday, all this quantity of electricity and all. Now, from what I said earlier, I told us that we have quantity of electricity, and that one is equals to high T. Your Q equals to high T, where this I is your current and this T is your time. So current in amperes, time in seconds. So Q is in coulombs. So Q is in coulombs, and then Q can also be in Faradays. Now there's what we call Faraday. After that Faraday, now there's what we call Faraday of electricity. So now what is Faraday? Let me define it by saying 1 Faraday is 1 F, and 1 Faraday is a quantity of electricity that produces 1 mole of an electron. Is a quantity of electricity that produces what? 1 mole of an electron. Quantity of electricity that produces 1 mole of an electron. That is 1 Faraday. So now, how many Faraday will produce 2 moles of an electron? 2 Faraday. So now, if I give you a reaction and I say Cu2 plus 2E minus to give you Cu solid. Now, from this reaction, okay, before I go to this, another thing. Faraday is actually the quantity of electricity that is like liberated to discharge 1 mole of a substance. Now, if you look at this now, this is a reduction reaction. Oxidation number of this one is +2. This one is 0. This reduction in oxidation number, +2 to 0. This reduction. Now, what has happened? Copper ion gains 2 electrons to become copper metal. So in this case, 2 electrons are being gained. Now, what will happen here is that if you look at this now, from this is 1 mole of the metal being deposited. 1 mole of the metal being deposited. Now, to deposit 1 mole of copper, how many electrons are being gained? 2. So, copper ion gains 2 electrons to deposit 1 mole of copper. And then don't forget I said Faraday is that quantity of electricity. 1 Faraday, quantity of electricity required to what? Produce 1 mole of something. Whether 1 mole of electron, 1 mole of a substance, 1 mole of a compound, 1 mole of anything. Now, for here now, that means to produce 1 mole of copper, we'll be needing how many Faraday? 2 from these 2E minus. So 2 Faradays will give us what? 1 mole of copper metal. Now, we can have another, let's use aluminum for example. Aluminum is always Al3 plus. Al3 plus 3E minus to give us Al. You can see 3 plus minus times 3, that's minus 3. 3 plus minus 3, that will give you 0. So that's why this one is carrying no charge. So oxidation number of this one is +3, this one is 0. This is also a reduction reaction. Now, this is 1 mole of aluminum, 1. So to give 1 mole of aluminum, how many Faradays? So we gain 3 electrons, meaning that 3 Faradays is needed. 3 Faradays are needed. So 3 Faradays of electricity will give us how many mole of aluminum? 1 mole. So for me to get 2 moles of aluminum, how many Faraday will I be needing? I'll be needing, so if 3 Faraday gives me 1 mole of aluminum, to get 2 mole of aluminum, that means I'll be needing 6 Faraday. It's as simple as that. 3 Faraday gives me 1 mole. To get 2 moles, what happens? Cross multiply. I will be needing what? 6 Faradays. That's just the way it is. Very simple. So now, let's say we have, now, the common equation that I said you guys should memorize the other time. 4OH minus anodic reaction. That was to give you 2H2O plus O2 gas plus 4E minus. Now, looking at this is 4E minus here. That means to get 1 mole of oxygen, 1 mole of oxygen gas, 4 Faradays of electricity are needed. So to make it simple for you, anywhere you see electrons, that coefficient in front of that electron, that's the number of Faraday needed for anything you want to do there. So how many Faradays do we have? 4 Faraday. So to get 1 mole of oxygen, how many Faraday will be needed? 4 Faradays will give you 1 mole of oxygen. It's as simple as that. So for anything you want to calculate, maybe mass, you just do this. Now there are some questions that are very common. Now, and then we go to that. We have, there are some elements like this. Let's say we have copper, 63.5. That's the atomic mass. Aluminium, 27. Sodium, 23. Oxygen, 16. And then many more. Yeah. We have silver. That one is 108. And then many more. Now, all these things that I'm writing here, those are the atomic masses of each of the elements. Atomic masses of each of the elements. Of an element, we weigh all these things that I'm putting here. So if I say Ag equals 108, what I'm saying is that 1 mole of silver, which is Ag, has a mass of what? 108 grams. So if I say, normally, silver is Ag plus. So to deposit 1 mole of silver, that would be Ag plus E minus to give us Ag solid. That is to say, 1 Faraday will give us 1 mole of Ag. I can still say that since 1 mole of Ag has a mass of 108, I can say 1 Faraday will give us 108 grams of Ag. I'm still saying the same thing. So let us quickly check the way some questions that we have here. So we use this principle to solve them. And then, I have a question here. So the question says, a solution of copper 2 TeS is electrolyzed. So the solution is copper 2 TeS, CuSO4. The solution is being electrolyzed with a current of 6 amperes. So I equals to 6 amperes. 6 amperes flowing for 5 hours. That means time is what? 5 hours. But don't make a mistake. You have to use the SI unit of time here, which is what? Seconds. That means you'll be converting 5 hours to seconds. How do you convert 5 hours to seconds? 60 minutes make 1 hour. Now, 60 seconds make 1 minute. So we can actually do it from here by using our chain reaction. So 5 hours times 1 over 1 hour equals how many minutes? 60 minutes. We are converting to seconds. We are going to seconds. Then we know that 1 minute, how many seconds are in 1 minute? 60. 60 seconds. So how do you convert 5 hours to seconds? 5 times 60 times 60. So you will not be given a scientific calculator in your JAMB, so you must know how to put you need to be very smart to get things like this very quickly. 60 times 60, that's 3,600. That's with the current of mass of copper deposited. Calculate the mass of copper deposited. Now, so they are giving us the question that 1F equals to 96,500 coulombs. That is the value of 1 Faraday. 1 Faraday equals to what? 96,500 coulombs. Now, they are asking us that a quantity of electricity of, current is 6 amperes, time is 5 hours. Now, from this, we can calculate the quantity of electricity here, which is Q times IT. So that means Q times T. Q equals to IT. So our Q equals to, what is our high? 6. What is our time in seconds? 180, 18,000 seconds. So if you multiply 18 times 6, that's 18 times 6. So that's what? 108. So that's what? We're having 108, 1, 2, 3. That's 108,000 coulombs. That's the quantity of electricity, 108,000 coulombs. And you know that for copper normally, from this CuSO4, you'll be liberating what? Cu2 plus what? SO4 2 minus. The question is asking you for the mass of copper that will be what? Liberated. Now, how do you do it? You know that copper is divalent because of these 2 plus. Now, so what is the equation? Cu2 plus 2E minus to give you what? Cu solid. That is to say, 2 Faradays will give us what? 1 mole of copper. 2 Faradays will give us 1 mole of copper. Now, what is the mass of 1 mole of copper? 65. They always give you in your question. So you will see in a bracket, so they put Cu equals to 63.5. This is the atomic mass of copper, meaning that 1 mole of copper has a mass of what? 63.5 grams. Now, so how do you do it? Cu2 plus 2e minus to give you Cu solid. 2 Faradays will give you 1 mole of copper. What is the mass of 1 mole of copper? 63.5. So you can write this and say that 2 Faradays will give you what? 63.5 grams. Now, from 1 Faraday is equals to what? 96,500 coulombs. So change this one to coulombs. 1 Faraday is equals to 96,500. So what will be 2 Faradays? Multiply by 2. So this may be what? 2 times 96,500 equals to 63.5 grams. Now, what is the quantity of electricity that we calculated here? 108. So if 2 times this one will give us 63.5, what will 108,000 coulombs give us? Equals to x. If we do it very well, what will be the answer? This one times this, that is to say our x will be equals to 108,000 times 63.5 over 2 times 96,500. So this cancel, you have cancelled this. Then you perform. So 2 here, if you press your calculator, what's going to be the answer? 108,000 times 63.5, everything divided by 2 times 96,500. So you'll be getting what? According to what we have here, approximately you'll be having 35.6 grams of copper. 35.6 grams of copper. That's how to do that. Now, let me give you another example. So let's do another one so that we have full understanding. So permit me to rub this side. Now we have the question says a current of 3 amperes. A current of 3 amperes. So what is the current? I, 3.0 amperes. Okay, let's continue. Passing for 4 hours. So the time is what? 4 hours. Don't forget, will you leave the time in hours? No. We need to convert to what? Seconds, because that's the SI unit of time. So the current is T, which is what? 4 hours. So how do you convert to seconds? 4 times 60 times 60. Okay, that will give us what? 4 times 60 times 60. That's what? 14,400 seconds. Good. Don't forget, let's do our Q. Q equals to what? IT. That is to say, that will be what? 3 multiplied by 14,400. And that one will give us what? 43,200. What will be the unit? Coulombs. Okay. Now, a current of 3.0 amperes passing for 4 hours through a molten tin salt. Tin salt. Tin. T-I-N. Tin salt. Tin has symbol SN. And then tin has symbol SN. So, it's actually divalent. It's actually divalent. Now, so a current passing this through this deposit. Now, they're asking us to calculate the mass of tin deposited. Mass of tin deposited. Now, from this equation, they've already given us the current. They've already given us the quantity of electricity. Because zinc is 2 plus, so we'll be having Sn 2 plus 2e minus to give us zinc solid. From this here, I've told you before that the coefficient in front of the electron, that will be the number of Faradays that we'll be needing to deposit 1 mole. So from here now, 2 Faradays will give us what? 1 mole of tin. Okay, now, and you see that now I can put Zn equals to 119. This is the atomic mass of tin, meaning that 1 mole of zinc has a mass of what? 119 grams. So if 2 Faradays give you 1 mole of zinc, that means that same 2 Faraday will give you, since 1 mole of zinc weighs 190 grams, you can still say that 2 Faradays equals to what? 119 grams of tin. Now, what mass will this one give you? 43,200. Convert this one to coulombs. Don't forget, 1 Faraday is equals to what? 1 Faraday equals to 96,500 coulombs. So this one will be what? 2 times 96,500 coulombs equals to 119. Then what will this one give you? 43,200 equals to x. So we can just solve it and get our x. Just as simple as that. Now, they might ask you a complicated kind of question that you might be like, okay, 3 Faradays. But you might be asked to calculate it. 3 Faradays. But you might be asked to calculate it. So how do you do it? that means we say that it is 1 Faraday that you need to deposit 1 mole of a substance. That means to deposit 1 mole of this substance, since it is X that is here, it is X that will be in front of this place. So that means X Faraday will be needed to deposit what? 1 mole of this substance. So I know that 1 Faraday is what? 96,500. So this place will be what? X times 96,500 equals to 1 mole of A. 1 mole of A. So we'll be doing a question that has something to do with this. Now, this is the question. 0.66 grams of a 0.66 grams of a divalent metal. 0.66 grams of a divalent metal. When they say divalent, they have already told you that that thing carries what? 2 plus on top. Meaning that what will be here is 2. So the question says 0.66 grams of a divalent metal M. So because M is divalent, that means it will be what? M2 plus. So divalent metal M is deposited when a current of 1.35 amperes. A current of 1.35 amperes. When a current of 1.35 amperes. So I equals to 1.35 amperes. Is passed for 1,500 seconds. Meaning our T is what? 1,500 seconds. Through a solution of its salt using inert electrodes, calculate the relative atomic mass of M. Calculate the relative atomic mass of M. So the question is very simple. 0.66 grams. I think it will be good for me to write the whole question so I can see it. So we have 0.66 gram of a divalent metal M is deposited when a current of 1.35 amperes is passed for 1,500 seconds through a solution of its salt using inert electrodes. Full stop. Calculate the relative atomic mass of M. Now, how do you approach this question? We have our I, 1.35 amperes. We have our T, 1,500 seconds. So calculate our Q equals to I T, which is equals to 1,000, which equals to 1.35 times 1,500 seconds. And this one will be giving us, so that's what? 2,000 and what? 35 coulombs. 2025 coulombs. Now, from what we said before, if you pay attention, 0.66 gram of a divalent metal. The metal is divalent, means that it carries a valency of what? 2 plus. So because it carries a valence of 2 plus, it needs how many electrons? It will be needing 2 electrons to get 1 mole. So because it needs 2 electrons, that means that's equivalent to what? 2 Faradays. So because it's divalent, so it will be M2 plus. M2 plus plus 2E minus to give us M solid. So what will happen? That is to say, from this 2E minus, that means 2 Faradays, will give us 1 mole of M. But they're asking us for the relative coulombs equals to 1 mole of M. Now let's go further. Don't forget that in the question it says 0.60 gram of divalent mass M is deposited upon while using this. Now we can go further and say the quantity of electron here is 2025. So 2025, they say that 2025 of this 2025 coulomb is giving us 0.66 gram of M. 2025 coulombs is giving us 0.66 gram of M. So we can go further and then solve the question. So from here we'll be having, sorry please. Maybe. Okay. Permit me to rub this side. Now, when I was explaining relative atomic mass to us that time, I said they can give you Al equals to 27. The meaning of this is that 1 mole of aluminium, what is the mass? 27 grams. That's the same thing they're asking us to find here. Now, but because they told us that the metal is divalent, that is 2F will give us 1 mole of that thing. That is to say, 2F, 2 Faradays will give us the mass of that thing. So that means, you know, if it is Cu2 plus now, plus 2E to give Cu, we say 2 Faradays will give us 1 mole of Cu. And because we know that 1 mole of copper is 63.5, so we just say that 2 Faradays will give us what? 63.5 grams. But in this case, we don't know this RAM. That's what we are trying to find. So since we know that 2 times 96,500 equals to 1 mole. So we can say that 2 times 96,500 equals to the relative atomic mass of that thing. Because the mass of 1 mole of an element, that is the relative, that's the atomic mass of the element. So since 2 Faraday equals to 1 mole of M, we can say that 2 Faraday is also equals to what? The mass of that 1 mole of M, which is the relative atomic mass. So you can just bring and say, what 2 times 96,500, that's what? 93,000. So we can say 193,000 equals to X gram. Now, for this one, what quantity of electricity gave us 0.66? 2025. So you can now say that 2,000 column is there. 2,025 columns equals to what? 0.66 gram. So we can solve this times this. So that means our X gram that we are looking for is equals to what? 193,000 times 0.66, everything over what? 2025. So X is equals to what? What will be the mass? Now from we calculate here, so if you do it well, the answer should be 62.9. So from here, X is what? 62 point what? The answer is 62.9. Now, approximately you can say X is equals to what? 63. X is equals to 63. So you can find an element that has the atomic mass of 63 and we get our answer. So just know that if they say something is univalent, that means that thing needs only 1 electron. Maybe it needs to gain 1 electron or lose 1 electron to form 1 mole of its normal atom. So that is to say, if that thing is univalent, 1 Faraday. If it is divalent, 2 Faradays. If it is trivalent, 3 Faradays. If it is tetravalent, 4 Faradays. Just as simple as it is. So if they say something is tetravalent, you can say, now from here, do you know why we said M2 plus and not M2 minus? Because 2 minus is also divalent, because it is 2. But they said that what? Of a divalent metal. Metals are what? Metals are reducing agent. They are electron donors. And when something donates electron, it becomes what? Positively charged. So that's why it is what? M2 plus. So that's how it is. So because of this M2 plus, if it's going to undergo reduction normally and give you the metal, it will be M2 plus 2E minus to give you what? M solid. So 2 plus and 2E minus here, so that you get your, so 2 Faradays to give you 1 mole of the metal. So that's how to solve questions like that. So if you check your JAMB, you'll be seeing a lot of questions, but according to your syllabus, they'll not be bothering you with much. But you can try as many questions as you want. But from what we have done so far, you must have been able to get the basic methods of dealing with questions that involve electrolysis. So let me just do a quick summary. We started from electrochemistry, electrolysis, breaking down when electricity passes through, breaking down of a chemical compound called electrolyte in molten form. Emphasis on what? Molten form. Now, so when electricity passes through, it breaks down and then releases ions. Then we talked about strong electrolytes and weak electrolytes. Strong electrolytes, they ionize completely. I gave examples like strong acids, strong base, our common salts. And then I said example of weak electrolyte, they ionize only partially. Example is water. Weak bases like ammonia, weak bases like sodium triisocarbonate 4, and then organic acids like your arganic acid, carboxylic acids, and even your normal acid like triisocarbonate 4, H2CO3 is a weak acid, and then your H2SO3 is also a weak acid. and many more like that. Then we went to talk about electrodes, the terminals that you have in your electrolytic cell: anode, cathode. At anode, oxidation. At cathode, reduction. Oxidation is what? Oxidation is the process of electron loss. Reduction is what? Electron gain. The reducing agent loses electron. Oxidizing agent gains electron. Oxidizing agent is also known as oxidant. Reducing agent is also known as what? Reductant. Now, let me give you, there's a common reaction. Like, let's say, let me give you this. 2Fe2 plus 2Fe2 plus Mn2 plus to give, no, 2Fe2 plus 2Cl minus to give you Cl2 plus Fe3 plus. Now, look at this. This is a very common, they usually ask questions about it. Now, this is ion 2 ion because of this 2 plus. This is chloride ion. This is chlorine gas. And this is what? Ion 3. Now, for you to, they can say that which of the following is reduced. In a redox reaction, you have oxidizing and reducing agent. Which one will be reduced? The oxidizing agent. Which one will be oxidized? The reducing agent. Which one loses electrons? Reducing agent. Which one gains electron? Oxidizing agent. So let's check. Don't forget, oxidizing agent is also, like oxidation is the process of increase in oxidation number, while reduction is the process of what? Decrease in oxidation number. Let's check. So from here, so we can say that since this one carries 2 plus, this one plus 2 plus 3. Let me put 2 in front because of the coefficients here. Plus 2, and then this one is 2. Okay. Let me just put, I don't need to balance it. Let me just remove this. Let me just do it like this. So this one is plus 2 to plus 3. This one is minus 2 to 0. Okay, it's not supposed to be. Let me just give another reaction. Let's say we have, let me give you Fe2 plus MnO4 minus to give us Fe3 plus Fe plus Mn2 plus. Now, the oxidation number of this one is plus 2. This one is plus 3. So whenever you have ions, whether positive ions or cations, if they are monoatomic, what do I mean by monoatomic? This is monoatomic. That is, your ion, in your ion, you have only one atom present. This one now is ion, just ion. Now, this one is polyatomic. Why? There's manganese atom inside, there's oxygen, more than one. So this is a polyatomic ion. But this one is what? Monoatomic. How many atoms are there? Just one atom of ion. This one too, monoatomic. But this one is what? Polyatomic. So whenever you have a monoatomic ion, the oxidation number is equal to the what? The charge carried on top. So if you have Fe2 plus, what's the oxidation number? Plus 2. Fe3 minus, what's the oxidation number? Plus 3. Mn2 plus, oxidation number is what? Plus 2. Now, from this place, manganese is what we are concerned about here. So let's calculate the oxidation number of manganese. Now, if you have an ion, whether monoatomic or polyatomic, the sum of everything inside will be equal to the ion on top. The sum of all the oxidation number. So everything here will be equal to minus 1. So I want to find out of manganese. So it will be Mn plus, how many oxygen atoms do you have here? 4. 4. Now, oxygen in most compounds has oxidation number of minus 2. So put minus 2 here. Minus 2. Everything equals to what? Minus 1 because of this minus that is here. If this one were to be 2 minus, it could have been equals to minus 2. But because this place is minus, so it's just minus 1. So this one will give us Mn minus 8 equals minus 1. Eventually, Mn is equals to what? Plus 7. Meaning that manganese is plus 7 here. And then it's becoming plus 2 in this place. Now, let's go. They can ask you that which of the ions is oxidized, which one is reduced. Now, from this case now, the reducing agent, don't forget that oxidation is increase in oxidation number. Reduction is what? Decrease in oxidation number. Are you getting me? Oxidation, increase in oxidation number. Reduction, decrease in oxidation. So we can see here, plus 2, Fe is here, Fe is here. So you can join this together. There's increase in oxidation number, plus 2 to plus 3. What do you call that? Oxidation. So this is oxidation. Now, because it's a redox reaction, there are only two things are possible: oxidation and reduction. Meaning that the second one will be what? Reduction. So you can see, manganese is taking plus 7 here. It's becoming what? plus 2 here. Oxidation number has what? Decreased. So this is what? Reduction. Now, it is a reducing agent that undergoes reduction. Sorry, it's a reducing agent that undergoes oxidation. Why oxidizing agent undergoes reduction? So a reducing agent causes reduction. Oxidizing agent causes oxidation. However, a reducing agent becomes oxidized, and oxidizing agent becomes reduced. That's the way it works. So from here now, we can see the oxidation number of iron here is moved from +2 to what? +3. That's oxidation, Abi. That means that this one has been oxidized to Fe3+. Fe2+ has been oxidized to what? Fe3+. So which one is being oxidized? Fe2+ is being oxidized, meaning that Fe2+ is the reducing agent, because the species that is being oxidized, that is the what? Reducing agent. The species that is being reduced, that is what? Oxidizing agent. So to this one, +7 to +2, that is reduction, Abi, meaning that MnO4- has been reduced from +7 to +2, meaning that this is the what? Oxidizing agent. That's how you do it. So now I can give you 3 things that are funny. Number 1, Fe2+ is being oxidized. That's correct. Fe2+ is a reducing agent. That's correct. Fe2+ is the reductant. Same thing. Now, looking at this place now, our Fe3+, after this one has been oxidized, we got this. Because they can just ask you, they be like, okay, which of the following is true? Number 1, Fe2+ is the oxidizing agent. That one is wrong. Why is it wrong? The oxidation number increased from +2 to +3. +2 to +3, that's what? Oxidation. Which species undergoes oxidation? Reducing agents. Because that is the reducing agent that is being oxidized. It is the process of something being oxidized. That's what we call oxidation. And then another method I can use to know is that, you know that metals lose electrons. Abi now, this one is +2 to +3, increase in oxidation number, right? But you can see that this one, when something is Fe2+, what does it mean? It has lost how many electrons? 2. But in this place, this one has lost how many? 3. Meaning that this one was losing 2 before, but after getting here, it loses 1 more to make it to have lost how many electrons? 3, making it a reducing agent, because it's a reducing agent that what? Lose electrons. So you can know from here that Fe2+ is the what? The reducing agent. How do you know? +2 to +3, increase in oxidation number. The species that its oxidation number increases, that is the what? Reducing agent. The species that the oxidation number is being reduced, is being decreased, that is the what? That is the oxidizing agent. That's how to know. It's very simple. And then there are common examples of oxidizing agents. Oxygen is a good oxidizing agent. Oxygen. For example, if you see your reaction, your carbon C plus O2 to give you CO2. Carbon is acting as a reducing agent. Oxygen is acting as what? Oxidizing agent. Oxygen is oxidizing carbon. This one is being, that means carbon, because carbon is a reducing agent, it will be what? Oxidized. Because oxygen is the oxidizing agent, it will be what? Reduced. So carbon is being oxidized to CO2. Oxygen is being reduced to CO2. Same thing. So anywhere you see oxygen, is always what? Oxidizing agent. So when you see oxygen and something, you know that, okay, this is oxidizing, the other one is reducing. Now, you can see, you can actually have 2 reducing agents in an equation. For example, let's say you have H2S plus SO2. This one to give you 2S plus 2H2O. Let me balance. So let's say we have is it 2? Let me put 2 here. 2H2O, 3S. Yeah. And then this is balanced now. Now look at this. Normally, H2S is a reducing agent. SO2 is also a reducing agent. But H2S is a stronger reducing agent than this. So in this case, this one becomes the reducing agent. This one becomes the more reducing agent becomes the really reducing agent. Why the